Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall study a relation between continuity and differentiability of complex valued functions. In our earlier lecture, we have defined derivative of complex valued function, and we have solved some examples as stating whether obtaining derivative, and second example we have solved in which the derivative does not exist. So, there are functions for which derivative exists or derivative may not exist, and we shall consider example here, and then we shall establish we shall see what is relation between continuity and differentiability of function. Consider an example as let we shall denote the function by w, and which is f of z is equal to mod z whole square. Then we shall show that this dw by dz exists when z is equal to 0, or exists at z is equal to 0, and dw by dz does not exist for z not equal to 0, or at z not equal to 0, and at the points z not equal to 0. So, this derivative only exists at 0, that we shall show, and does not exist when z is non-zero. So, we will have this w is equal to, we have w is mod z whole square, and therefore, we shall find out delta w. Delta w is f of z plus delta z. In the definition of derivative, we have defined what is we have used the notation what is delta w and delta z. So, these are increments in w, which is f of z plus delta z minus f of z, and if this is divided by delta z, its limit as delta z tends to 0 is the derivative. So, this is equal to delta w we are obtaining, and or otherwise we can write the limit derivative directly. We have this. So, and dw by dz is equal to limit delta z tends to 0. This is actually this is the derivative definition. So, z plus delta z minus f of z divided by delta z. So, without using this delta w notation, directly we can write the derivative. dw by dz is limit delta z tends to 0 of this, and but what is f of z plus delta z? This is equal to limit delta z tends to 0, f of z plus delta z, this is f of z mod z whole square, and therefore, f of z plus delta z will be mod of z plus delta z square minus mod z square divided by delta z, or this is equal to limit delta z tends to 0, and this mod z square we can write z into z bar, conjugate of z. So, therefore, this will be z plus delta z into conjugate of z plus delta z minus, similarly mod z square is z bar divided by delta z, using this property of modulus of z, and this is equal to, this is limit delta z tends to 0. We expand this, or before expanding we can write like this z plus delta z. This is using again the property of conjugate z bar plus delta z bar. Conjugate of z1 plus z2 is conjugate z1 plus conjugate z2 minus z bar divided by delta z. and we multiply now this is limit delta z tends to 0. So, what is the product is z bar, z delta z bar, or we will write plus z bar into delta z. I am writing this product plus then next also delta z, conjugate of delta z into delta z, terms of delta z I have written. Now, what remains is z into delta z bar, z into delta z bar, and delta c. So, 4 terms we have written, minus z bar whole divided by delta z. You check this product, and further this will be equal to limit delta z tends to 0. Now, the first and the last term cancels, positive and negative, and what about remaining terms we divide by delta z each, and this becomes z bar, this becomes z bar plus this becomes delta conjugate of delta z, and this is the plus, this will remain as it is, and that is z, we will write z conjugate of z delta z divided by delta z. So, thus this is what is the derivative dw by dz. And now we want to find this limit as delta tends to 0, and we know this delta tends to origin, tends to origin by any manner and not a particular direction. But what happens here is this conjugate of delta z will be different when delta z tends to 0 along real axis and delta tends to 0 along imaginary axis. So, this has different values. So, that we shall state first. Now, if delta z is, so we will suppose this as 1. If delta z let be 0 0, delta z be delta x comma delta y, delta z be delta x comma delta y, and delta z approaches 0 means will approach towards 0 0, and let delta z be on real line. We will consider first delta z on real line, and on real line this imaginary component is 0, delta z is delta x comma 0 be a point, or this is delta x plus I into 0 be a point on the real line, real axis, on the real axis, and delta z approaches 0 0. Then we have conjugate of delta z. Conjugate of delta z means conjugate of this, conjugate of delta x plus I into 0, and this is delta x. This actually we have done in our earlier example, in earlier lecture, second example, delta x minus I into 0, or that can be written as delta x plus I into 0. It is same as 0, and this is same as delta z. So, delta z is conjugate of delta z is equal to delta z if z approaches origin along the real axis, and let delta z be 0 comma delta y, that is 0 plus I into delta y be a point, on the imaginary axis. That is y axis, and delta z tends to 0 0. In this case, we have, see, the conjugate of delta z is equal to conjugate of 0 plus I into delta y, and that is 0 minus I delta y, or which can be written as minus of 0 minus plus I delta y, and this is minus delta z. You verify this. Conjugate of 0 plus I delta y is 0 minus I delta y, and minus sign is taken common, and this is again delta z. So thus conjugate of delta z has two different values. It is equal to delta z when the point delta z approaches origin along real axis, and it is equal to negative of delta z when delta z approaches 0 0 along imaginary axis. So therefore, because this delta z, conjugate of delta z has two values, we will have two limits here, and therefore from 1 we will write from 1 we have dw by dz is equal to limit delta z tends to 0. This is we will use the first case, delta z bar, conjugate of delta z is equal to delta z. This is z bar will remain as it is, and conjugate of delta z is now delta z plus z, and conjugate of delta z is same as delta z divided by delta z, or this will be, this is 1, and thus this is equal to z bar plus delta z is 0, and this is 1. So z bar plus z when delta z is delta x comma 0, when delta z is equal to delta x comma 0, that is delta z is on real axis, a point on real axis, and dw by dz is equal to limit delta z tends to 0. This is delta z tends to 0. Because we are having the two values of conjugate delta z, we will write the two limits from 1. So this is z bar plus, now what is the value of this in the second case? It is negative of delta z. So this is negative of delta z, and this is negative of delta z means minus z into delta z divided by delta z, or this is equal to, and now put the limit as the delta tends to 0. So this will be 0, this is 1, and what we will get is z bar minus z when delta z is equal to 0 comma delta y. So thus we have 2 and 3, the limit dw by dz, derivative of w with respect to z is z bar plus z, and in the second case dw by dz is z bar minus z. But we know if the limit exists or the derivative exists, it must be unique. But if dw by dz exists, then it must be unique. If the limit exists or this limit exists, then it must be unique, and therefore from 2 and 3 we have these two are equal, and that is z bar plus z is equal to z bar minus z. And what this gives, see, z bar on both sides cancels, and what we get is z is equal to negative z, or that is 2z is equal to 0, or z is equal to 0. So thus dw by dz exists if and only if, or if z is equal to 0. Thus dw by dz exists at z is equal to 0, and its value is and dw by dz. So at z is equal to 0, the value is, see, this limit or this value or this value, z is 0, z bar is 0. So it is 0 plus 0 or 0 minus 0 is 0, and at this is the value. And further we see that dw by dz does not exist when z is not equal to 0, since when z is not equal to 0, this z plus z bar, these two cannot be equal, since when z is not equal to 0, z bar plus z is not equal to z bar minus z. The two limits are different when z is not equal to 0. So thus this derivative of mod z square exists only at 0 and nowhere at other point. Thus so we have shown that this derivative exists at origin only, and it does not exist on other point, means it does not exist in the neighborhood of 0 also. So dw by dz exists at 0 and does not exist in the neighborhood of 0. So we write as a remark, let f of z can be written as in the component functions u x comma y plus I v x comma y, and if f of z is equal to mod z square, now what will be u and v? Mod z square, z is x plus I y and mod z square is x square plus y square, and therefore this is x square plus y square into I 0, and therefore in this case u is equal to, u is this function x square plus y square and v is 0. And we have seen just here as this f of w is mod z square and its derivative exists at 0 only and no other point. So this thus we have seen from above example, or we have seen that this derivative, therefore the derivative of this f of z, f dash z, exists at z is equal to 0 and nowhere in the neighborhood of 0. See, and but these component functions u and v has continuous partial derivatives at of every order, but the functions component functions u is equal to x square plus y square and v is equal to 0 has continuous partial derivatives, as partial derivatives, or you may write has partial derivatives. The partial derivatives of this exist with respect to x and y, but this function is not differentiable. Partial derivatives exist at every point, but the derivative of f of z does not exist except 0, has partial derivatives. Of all order. And thus a function has, and what about the continuity of f of z, has these partial derivatives are continuous, has, see, continuous partial derivatives. Also f of z, also f of z is equal to mod z square is continuous at all points. but it is not differentiable at all points. But it is not differentiable except at 0, at z is equal to 0. So this function is continuous everywhere, but this function is not differentiable, not differentiable except at 0. So this we have seen, it has derivative at only z is equal to 0 and nowhere else. So that this is a kind of relation between continuity and differentiability, continuous everywhere but not differentiable everywhere. Now we will have a result as stating a relation between continuity and differentiability. A differentiable function is continuous if a function f of z is differentiable at point z0, z is equal to z0, then it is continuous at point z is equal to z0. So that means differentiable function implies continuous function. That is easy to prove. And let it is differentiable at z is equal to z0. So proof of this, here let function is differentiable, f dash of z0 exists. We have to prove the function is continuous at z is equal to z0, and therefore we shall consider limit z tends to z0 of f of z minus f of z0, and this we shall express as limit z tends to z0 f of z minus f of z0 divided by z minus z0 and multiplied by z minus z0. We have actually divided and multiplied by z minus z0, the value remains same, and this happens because z is not equal to z0, z approaches z0. This is, and now separate the limit using theorem on limit z tends to z0 f of z minus f of z0 divided by z minus z0, first limit, into limit z tends to z0 of z minus z0. And now you see what is first is exactly the derivative of f at z0. So therefore this is f dash at z0, and what about the second, z is approaching z0, so therefore this is 0, and this is existing quantity multiplied by 0 is 0. So thus what we have is the limit f of z minus f of z0 is 0, or what is the left side, that is limit z tends to z0 of f of z minus f of z0 is equal to 0. So this implies limit z tends to z0 of f of z is equal to limit of f of z0, but this is a fixed quantity and therefore it is f of z0, and this is the definition of continuity. If this limit exists and these are equal, then the function is continuous at z0. So this shows that f of z is continuous at z is equal to z0, and thus a differentiable function is continuous. That we have proved. The function is differentiable, then it is continuous, but the converse is not true. That is earlier we have seen f of z is mod z square is continuous at all points, but not differentiable except at z is equal to 0. So this means differentiability implies continuity, but continuity does not imply differentiability. The converse of this result is not true. The converse of this result is not true. and this is the counter example for this. It is sufficient to show that continuity does not imply differentiability. So thus differentiability implies continuity, but continuity does not imply differentiability. This is the relation between the continuous functions and differentiable functions. So I hope you will understand this. Thank you for watching the lecture.